The multiple testing problem is the problem of deciding how to deal with the fact that if enough hypothesis tests are done, some of them will be positive even if all of the null hypotheses are true. For example, consider the admittedly peculiar question of whether the Fahrenheit temperature in New York City, rounded to the nearest integer, tends to be an odd number. It is likely, of course, that there is no particular tendency for the integer temperature to be either an odd number or an even number, so the expected proportion of temperatures that are odd numbers is 50%, which is the null hypothesis for this test. If a test of that hypothesis is repeated enough times, however, it is possible to eventually find a sequence of temperatures with an unusually high fraction of temperatures that are odd numbers. This input, for example, returns temperatures in New York City during 3 days in January of 2012 when 63 of the 93 measurements, or just over 2/3 of the measurements, were odd numbers. A hypothesis test for the population proportion can be done using the formulas from an earlier section, which leads to a very small p-value of about 0.06%, which at a significance level of 5% is a positive result and leads to the conclusion of rejecting the null hypothesis. Since it is unlikely that there is any real tendency for temperatures to be odd numbers, this result is probably a false positive. The probability of at least one false positive in a set of hypothesis tests is called the family-wise error rate, commonly abbreviated FWER. If the number of hypothesis tests is large, the family-wise error rate can be quite high. The probability of a false positive if the null hypothesis is true is the level of significance alpha. So, following basic rules of probability, the probability of not getting a false positive is 1 minus alpha. The probability of not getting any false positives in 100 tests is 1 minus alpha to the 100th power, and the probability of at least one false positive, which is the family-wise error rate, is 1 minus that probability, which turns out in this example to be something over 99%. So in 100 hypothesis tests with a significance level of 5%, there is more than a 99% chance of at least one positive result, even if there is nothing of significance to be detected. A simple way of lowering the family-wise error rate is to use a smaller value for the significance level. A common way to do that, called the Bonferroni correction, is to divide the significance level by the number of tests. In this example, the number of tests is 100. Dividing the significance level of 5% by 100 leads to a family-wise error rate of just under 5% for 100 tests. The main problem with this approach is that dividing the significance level by 100 gives a significance level for each test that is so small that very few tests will give positive results, and so there may be many false negatives. In recent years, several different methods, including a method called the Holm-Bonferroni method, another method called the Benjamini-Hochberg procedure, and other methods have been introduced, all with the goal of controlling the number of false positives in multiple hypothesis tests without giving too many false negatives. A long-established standard for checking almost any scientific conclusion, however, is replicability, which is whether or not some equivalent independent test leads to the same conclusion. The suggestion that temperatures in New York City tend to be odd numbers can be tested by starting with different but equivalent data. For example, shifting the 3-day period of time in the previous input by a few hours gives much different data. The size of this new data set is the same as the size of the previous data set, but the fraction of odd numbers in this data set is much smaller. And repeating the earlier calculation to do a test of the hypothesis that the population mean is 0.5 gives a p-value of more than 25% rather than 0.06%. So the null hypothesis is not rejected, and the conclusion that temperatures tend to be odd numbers is not reproduced.